Welcome back to CTN. I'm Robert Van Slooten. This is a continuation of 8 Queens on a Chessboard. I'm going to start with the output of the project that I'm going to discuss. If you take the previous 8 Queens implementation and you modify it so it runs through all the possible board solutions, you'll find that there's 92 of them. However, a solution can be rotated, and you can ask yourself, well, does the rotation actually represent a unique solution? It turns out if you deal with that, if you actually want to find all the ones that don't rotate that are unique, in other words, the rotation is the same as the one you began with, you'll find there's 24 unique solutions. Now the arithmetic there doesn't quite add up, but I will explain why that happens. Now what you see here is there's a key. I use that for some storage and access and so on, mostly to deal with eliminating rotations. And there's 24 boards represented here. Now 2 of these boards have a unique symmetry. And that's going to be the subject of the next slide. And that accounts for the math issue. So let's move on. Okay, I have 4 copies of one of these boards with the symmetry. And I'm going to rotate the upper right-hand one 180 degrees. Now these 2 boards are the same on the top. I'm going to go to the bottom. I'm going to rotate the left one by 90 degrees. A little hard to read because the character's on the side. But I'm going to rotate the one on the right of it by 270 degrees. We have 2 equal boards, and the angles are given. This is the board that has the same symmetry. All right. Now, if you do the arithmetic, I have 22 boards with 4 rotations total, including the initial one. And I have 2 boards with only 2 valid rotations. So hence the 92. Let's go to the project. The implementation is a Mac OS terminal project. I'll be talking about the terminal in the next episode. Let's go ahead and run this. The output is the same thing you saw before. Now I have 3 files. I have a main, I have a Q8, and I have a board. The main is displayed here. All it simply does is create a Q8. It says find solutions, which is the recursive function, and it says print solutions. That produces the output down here. Q8 is really where the algorithm is actually executed. There's only one instance of it. It's a structure. There's a board, which is a structure which defines a board. There's multiple instances of boards because there's multiple unique solutions which are stored. There's the primary board where the algorithm actually operates on, and then there's temporary rotations of a board which are analyzed. Let's go ahead and look at the board first. The board.swift file defines the board structure. Now keep in mind there will be multiple instances of this structure because they're the solution, collections of the unique solutions. There's the main board that's actually being operated on, and there's also temporary boards. In the file, there's a constant defined, which is a 8x8 array of zeros. Now, within the structure, there's an array which represents the particular board, this particular instance of the structure. The directive, the keyword private, is used twice in this implementation, and that hides the data representation from the outside world. In computer science, it's called data encapsulation. That's a different subject. So every operation is a function. There's three basic functions. You're going to place a queen on a board, you can remove a queen from a board, or you can print the board. There's a test function, and you saw this in the previous episode, where you're determining whether the placement of a queen on the board is valid. Whether, by looking at the row, looking at the column, and looking at the diagonals. All right, these are two key functions for the algorithm. There's a notion of the ability to rotate a board. Take the existing board and return a new board. In other words, you're not actually rotating the board you're operating on. You're creating a board which is the rotation of that board. So it returns a board. And that's primarily an issue of interchanging rows and columns. You can analyze this yourself. There's a get key. For a particular board, you can take a string representation which represents that board. So you have a key, it's a string, it's also hashable. So if you think about that, you could use that for sets or dictionaries. And between those two concepts, you could determine the uniqueness of a board or the uniqueness of its rotations. There's a has symmetry, and I'm going to discuss that after I do Q8. Okay, Q8 has a board. It's the primary board, very similar to what you saw in the previous episode. Going down here, I have a counter, and that's actually a counter for the number of non-unique solutions, the 92 that you end up with. And I have a dictionary, which is keyed on a string, which is actually the key for a particular board, which you saw earlier. And what is stored is the boards, the actual structure for the boards, which we already covered. Now you may think that the problem can be dealt with as a set. And that's true. Sets they all have to be unique. There can't be duplicates. A dictionary is similar. They both key on a hashed value, and there can only be one instance of a particular hashed value. All right, now if you treat a dictionary carefully, you can treat it as a set. The benefit of the dictionary is you can also store, in this case, the board. And I want the board later because I want to do an operation on it to test symmetry, and I also want to be able to print it. Now I could build a new board from the key value, but I really didn't want to write that function. It's easier just to store the board. I have a function that says, is it unique? And I'm actually going to is a particular board unique? Has it already been placed in the dictionary? I'm going to come back to that in a minute. I'm going to go down to the recursive function, find solutions. The stopping conditions column 8, you've seen that before. I simply up the counter, and I do a test to say, is unique, the above function. If it is, I put it in the dictionary. Okay, based on the key and the data value that I'm putting in there is the board that I'm currently working on. Now let's take a look at unique. What do I really want to know? I want to create a temporary board. In other words, I want to copy what the current board is. And I want to do 3 rotations. All right. I want to determine whether any one of those rotations has already been seen. So I'm going to do a rotate, and you realize that the next time I iterate through the loop, I'm going to do another rotate. So it's going to go 90, 180, and 270 degrees. And I look for the board in the dictionary. If I get a null back, in other words, it doesn't exist, I'm going to simply return from the function. So I'm not going to continue in the loop. If I find one rotation which isn't unique, I'm going to return. Otherwise, I simply say it is unique, and that's when it gets placed in the dictionary. Now, in terms of the recursive loop, I'm going through 8 times, 0 to 7. It's very similar to what you've seen before, but you'll notice that the recursive function has no return value. So what I'm doing is I'm letting this run until it gets exhausted. It can't do any more permutations of the board to find solutions. Okay? So the stopping condition is I'm done. Column 7 is all the way up to the top, and I can't go back, and I end up returning all the way back to the top. Okay, I have a print solutions, and what that does is it says, all right, just print the numbers. Print the number of solutions, the 92, that don't take into account rotations. And I print the 24, which is actually the count of the number of things in the dictionary. I want to actually print the boards, but I want to do something additional. Under them, if I find symmetry, I want to be able to indicate that. That's actually done after the printing of the board. Now, here's the thing. If you ask for the keys of a dictionary, you'll actually get the keys back. The values, in this case strings, that were the original keys. What ends up happening is that ends up returning a set. It's not ordered. If you take the set and you say sorted, it's actually going to sort those key values. The reason I want that is because I want the board's output in some form of a sequence. I want them to make sense relative to each other. All right. Now, I have the loop. It's looping through that result. It's getting a temporary board. It looks it up, goes in the dictionary, and gets it based on the key. I want to print the key. That's what you see above the board printouts. And I want to say print array, in other words, for the board, so that actually outputs the board. Now, keep in mind that when you actually ask the dictionary for something, it's an optional value because it may not exist. So the optional value has to be unwrapped, and that's what the exclamation mark does. And that's why the test in unique, when it tests for null, that's the way it actually works. Let me see if I can find that. Okay, not equal to null. All right. Then what happens is, at this point, I want to take the temp board and I want to ask it if it has symmetry. All right. If it has symmetry, I want to print the fact that it does. That's the whole thing. I'm going to jump back to the board and I'm going to talk about has symmetry. All right, back to has symmetry. It's going to return a bool. In other words, it is symmetrical or it isn't symmetrical. I'm going to simply, in temp board, just copy self. I'm going to create an array which is going to have 4 keys in it. The key for the board itself and the 3 rotations. So I place in the 0 position in the array the current board, get key, and I'm going to do a for loop with 3 iterations, 3 rotations. I'm simply going to store the key for those rotations. Then I can do a check. There's several analyses you could do, but basically this just says that the board itself is the same as the 180-degree rotation, and the 90-degree rotation is the same as the 270-degree rotation. That's it. I just want to make one correction. When I talked about the board, I said null. It should be nil. Let's go to the photo. Thanks for watching.